Section 1.1, Functions. In this section, we're going to make sure that you're familiar with functions and function notation. Both will appear in almost every section in a calculus class, so you will need to be able to deal with them. First, what exactly is a function? The simplest definition is an equation will be a function if, for any x in the domain of the equation, the domain is all the x's that can be plugged into the equation. The equation will yield exactly one value of y when we evaluate the equation at a specific x. This is usually easy to understand with an example. So for example 1, it says determine if each of the following are functions. The first one is y is equal to x squared plus 1. This first one is a function. Given an x, there is only one way to square it and then add 1 to the result. So no matter what value of x you put into the equation, there is only one possible value of y when we evaluate the equation at the value of x. Part B, y squared equals x plus 1. The only difference between this equation and the first is that we move the exponent off the x onto the y. This small change is all that is required in this case to change the equation from a function to something that is not a function. Now, to see that it is in a function is fairly simple. Choose a value of x, let's say x equals 3, and plug it into this equation. So if we plug 3 into this equation, y squared equals 3 plus 1, which is equal to 4. So y squared is equal to 4, and that tells us that there are two possible values of y that we could use here. We could use y is equal to 2 or y is equal to negative 2. Since there are two possible values of y that we get from a single x, this equation isn't a function. Note that this only needs to be the case for a single value of x to make an equation not be a function. For instance, we could have used x is equal to negative 1, and in this case, we would get a single y is equal to 0. However, because of what happens at x equals 3, this equation will not be a function. Next, we need to take a quick look at function notation. Function notation is nothing more than a fancy way of writing the y in a function that will allow us to simplify notation in some of our work a little. Let's take a look at the following function. Y is equal to 2x squared minus 5x plus 3. Using function notation, we can write this in any of the following. F of x is equal to 2x minus 5x plus 3. We can say h of x is equal to 2x squared minus 5x plus 3. W of x is equal to 2x squared minus 5x plus 3. G of x is equal to 2x squared minus 5x plus 3. Capital R of x and y of x. Now recall that this is not a letter times x. This is just a fancy way of writing y. So why is this useful? Well, let's take the function above or in the previous page, and let's get the value of the function at x equals negative 3. Using function notation, we represent the value of the function at x is equal to negative 3. So we're looking for x is equal to negative 3 as f is equal to negative 3. Now the function notation gives us a nice compact way of representing function values. Now how do we actually evaluate the function? That's really simple. Everywhere we see an x on the right side, we will substitute whatever it is in the parentheses on the left side. For our function, it gives us this. So f of negative 3 is equal to 2 times negative 3 squared minus 5 times negative 3. And then we're going to follow order of operations. Negative 3 squared is positive 9. And then negative 5 times negative 3 is positive 15. So 2 times 9 is 18 plus 15 plus 3 gives us 36. Now let's take a look at some more function evaluation. So for example 2, we're given the following function, f of x, which is equal to negative x squared plus 6x minus 11, and we're going to find each of the following. So the first thing we're going to do is find a, which is f of 2. So we're going to plug it into this formula. So it's going to be negative times 2 squared plus 6 times 2 minus 11. Well, this gives us negative 3, because this is negative 4 plus 12 minus 11, which is equal to negative 3. Next we want to do is we want to find f of negative 10. So we're going to plug negative 10 into that function. So we're going to plug in negative 10 for all the values of x. So we get a negative times a negative 10 squared, which is negative 100. 6 times negative 10 is minus 60, and negative 11 is minus 11. So adding those together gives us negative 171, but make sure to be careful when squaring negative numbers. In part C, t becomes the input, so we're going to replace all the x's to be t. So this is negative t squared plus 6t minus 11. Remember that we substitute for the x's whatever is in the parentheses on the left. Often this will be something other than a number. So in this case, we put t's in for all the x's on the left. Part D, we're plugging in t minus 3 in for the value of x. So here is negative t minus 3 squared plus 6 times t minus 3 minus 11. So recall that you're going to have to do the FOIL method of t minus 3 squared. So it's going to be negative times t minus 3 squared plus 6 times t minus 3 minus 11. So let's go ahead and do that example here. So we have negative t minus 3 times t minus 3 plus 6 times t minus 3 minus 11. So remember, this is the FOIL method, so this is going to give you t squared minus 3t minus 3t plus 9 plus 6 times t minus 3 minus 11. And then we can distribute the minus sign. So we have negative t squared plus 3t plus 3t minus 9 plus 6t minus 18 minus 11. And now when we combine like terms, we should get negative t squared plus 12t minus 38. Next, in part E, we're going to evaluate the function of x minus 3. So again, doing the same thing here, we have negative x minus 3 times x minus 3 plus 6 times x minus 3 minus 11. And again, using the FOIL method, we get negative, this is x squared minus 3x minus 3x and that's plus 9 plus 6 times x minus 3 minus 11. If we distribute the sign, we get negative x squared plus 3x minus 9. Distribute the 6, we get 6x minus 18 minus 11. So we would get negative x squared plus 12x minus 38. Now in that previous example, the only difference between this one and the previous one that we worked out was we changed a t to an x. Other than that, there is absolutely no difference between the two. So don't get excited if an x appears inside the parentheses on the left. Part F, we can see that the input is 4x minus 1. So again, let me go ahead and do the work up here. So we have negative 4x minus 1 times 4x minus 1 plus 6 times 4x minus 1 minus 11. So we're going to get negative, we should get 16x squared minus 4x minus 4x plus 1 plus 6 times 4x minus 1 minus 11. Distributing the negative sign, we get negative 16x squared plus 4x plus 4x minus 1 plus 24x minus 6 minus 11. So when we combine like terms, we get negative 16x squared. We get plus 32x. And then we get minus 18. So this one is not much different from the previous part. All we did was change the equation that we were plugging into the function, which was 4x minus 1. And we plug that in for each value of x. All throughout calculus course, we will be finding roots of a function. A root of a function is nothing more than a number for which the function is 0. In other words, finding the roots of a function g of x is equivalent to solving g of x is equal to 0. So for example 3, we're going to determine all the roots of f of t, which is equal to 9t cubed minus 18t squared plus 6t. So the solution, we will need to solve this equation. We have 9t cubed minus 18t squared plus 6t, and then we're going to set that equal to 0. Now the first thing we want to do is we should factor the equation as much as possible. So what can we factor out of all three terms? Well, the greatest factor that we can factor out is 3t. So if we factor out 3t, what's left in here is 3t squared minus 6t plus 2, which is equal to 0. Next, recall that if a product of two things are 0, then one or both of them had to be 0. This means that 3t is equal to 0, or 3t squared minus 6t plus 2 is equal to 0. Now, if we look at the first equation here, it's clear that one of the roots must then be t is equal to 0. To get the remaining roots, we will need to use the quadratic formula on the second equation. Doing this gives the following. So here's our equation. We have 3t squared minus 6t plus 2 is equal to 0. So what do we know? We know that the value of a is equal to 3. The value of b is equal to negative 6. And the value of c is equal to 2. And now recall that the quadratic formula is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So what do? We plugged in the following values. So we said that 6 is plugged in for b. And then we can say that a represents 3. So there's our 3. And then c is 2. So there's 2, and then there's 2. So a negative times a negative makes us positive 6, plus or minus negative 6 squared is 36, minus 24, which gives us 12 divided by 6. Now keep in mind that 12 can be broken down as 4 and 3. So the square root of 4 gives us 2. So we have 6 plus or minus 2 times the square root of 3. And then we can simplify the 6's into 2's. So we can see that 2 goes into all of these numbers. So 2 goes into 2 one time, 2 goes into 6 3 times, and 2 goes into 6 3 times here. And then we can rewrite this as 3 over 3, which is 1, plus or minus 1/3 times the square root of 3, and which is equal to 1, or plus or minus 1 over the square root of 3. Now, in order to remind you how to simplify radicals, we gave several forms of the answer. To complete the problem, here's a complete list of all the roots of this function. T is equal to 0, t is equal to 3 plus the square root of 3 over 3, and t is equal to 3 minus the square root of 3 over 3. Note, we didn't use the final form of the roots from the quadratic. This is usually where we'll stop with the simplification for these kinds of roots. Also note that, for the sake of the practice, we broke up the compact form for the two roots of the quadratic. You will need to be able to do this, so make sure that you can. In the previous video example, I had a couple of points other than finding roots of a function. The first was to remind you of the quadratic formula. This won't be the last time you'll need it in this class. The second was to get you used to seeing messy answers. In fact, the answers in the above example and that example from the previous video are not really all that messy. However, most students come out of an algebra class very used to seeing only integers and the occasional nice fraction as answers. So here's a fair warning. In this class, I often will intentionally make the answers look messy just to get you out of the habit of always expecting nice answers. In real life, whatever it is, the answer is rarely a simple integer such as 2. In most problems, the answer will be a decimal that came about from a messy fraction and/or an answer that involved radicals. One of the more important ideas about functions is that of the domain and range of a function. In simplest terms, the domain of a function is a set of all values that can be plugged into a function and have the function exist and have a real number for a value. So for the domain, we need to avoid division by 0, square roots of negative numbers, logarithms of 0, and logarithms of negative numbers. If not familiar with logarithms, we're going to take a look at them a little later. The range of a function is simply the set of all possible values that a function can take. Let's find a domain and range of a few functions. So for example 4, we're going to find a domain and range of each of the following functions. So for part A, f of x is equal to 5x minus 3. We know that this is a line and that it's not a horizontal line because the slope is 5 and not 0. This means that this function can take on any value, and so the range is all real numbers. Using mathematical notation, this is the range, which is equal to left parenthesis negative infinity to positive infinity right parenthesis. This is more generally a polynomial, and we know that we can plug any value into a polynomial, and so the domain in this case is also all real numbers. Or we can say that x is going to be in between negative infinity and positive infinity, or we just write that as left parenthesis negative infinity comma infinity right parenthesis. Let's take a look at the next example, part B. G of t is equal to the square root of 4 minus 7t. This is a square root, and we know that square roots are always positive or 0. We know then that the range will go from 0 to infinity. Now, for the domain, we have a little bit of work to do, but not much. We need to make sure that we don't square roots of any negative numbers. So we need to require that what's under the radical is the radicand, which is 4 minus 7t, and it must be greater than or equal to 0. So we're going to solve for t by, we can add 7t to the right side, and then divide both sides by 7. So that means that t is less than or equal to 4 over 7, or we can write it as t is less than or equal to 4 over 7. So the domain is then the following. The domain being t is less than or equal to 4 over 7, or left parenthesis negative infinity comma 4 over 7 with the bracket because we need to include that value because of the equal sign. Part C, it says h of x is equal to negative 2x squared plus 12x plus 5. Here we have a quadratic, which is a polynomial. So we again know that the domain is all real numbers, or in this case, domain is x is in between negative infinity and infinity, or we're going to write that in interval notation, left parenthesis negative infinity, comma infinity parenthesis. In this case, the range requires a little bit of work. From an algebra class, we know that the graph of this will be a parabola that opens down because the coefficient of the x squared is negative. And so the vertex will be the highest point on the graph. If we know the vertex, we can then get the range. The vertex is then x, which is equal to negative 12 in the numerator over 2 times negative 2, which is equal to 3. So we know the value for x is going to be 3, and then we're going to plug 3 in for the value of x to find out what that y is. So we're going to get negative 2 times 3 squared plus 12 times 3 plus 5, which is equal to 23. So the ordered pair is 3, 23. So the 23 is the y value, which is the largest value of that function, which is the maximum. So as discussed, we know that this will be the highest point on the graph or the largest value of the function, and the parabola will take all the values less than this. So the range is then parentheses negative infinity comma 23 with a bracket. Part D, f of z is equal to the absolute value of z minus 6 minus 3. This function contains an absolute value, and we know that absolute value will be either positive or 0. In this case, the absolute value will be 0 if z is equal to 6. And so the absolute value portion of this function will always be greater than or equal to 0. We are subtracting 3 from the absolute value portion, and so then we know that the range will be the following, bracket negative 3 comma infinity. Now we can plug in any value into an absolute value, and so the domain is once again all real numbers. So we can say left parenthesis negative infinity, comma, infinity, right parenthesis. Part E, g of x is equal to 8. This function may seem a little tricky at first, but it is actually the easiest one in this set of examples. This is a constant function, and so any value of x that we plug into the function will yield a value of 8. This means that the range is a single value, or the range is just 8. The domain is all real numbers, so it would be left parenthesis negative infinity, comma, infinity, right parenthesis. In general, determining the range of a function can be somewhat difficult. As long as we restrict ourselves down to simple functions, some of which we looked at in the previous example, finding the range is not too bad, but for most functions it can be a difficult process. Because of the difficulty in finding the range for a lot of functions, we had to keep those in the previous set somewhat simple, which also meant that we couldn't really look at some of the more complicated domain examples that are liable to be important in a calculus course. So let's take a look at another set of functions, only this time we'll look for the domain. So we're going to take a look at another set of functions, only this time we're going to just look for the domain. So for example 5, we're going to find the domain of each of the following functions. The first function, f of x, is equal to x minus 4 over x squared minus 2x minus 15. So this problem, we need to avoid division by 0. So we need to determine where the denominator is 0, which means solving this equation and setting it equal to 0. So we have x squared minus 2x minus 15. We can factor that to be x minus 5 times x plus 3, which is equal to 0. Now solving both of them for x yields x is equal to negative 3, or x is equal to 5. So these are the only values of x that we need to avoid, and so the domain is the following. The domain is all real numbers except x is equal to negative 3 and x is equal to 5. Part B, g of t is equal to the square root of 6 plus t minus t squared. In this case, we need to avoid square roots of negative numbers. And so we need to require that we're going to set what's under the radical to be greater than or equal to 0. Now what we want to do is, we want to make sure that the negative t squared becomes a positive. So if we change all these signs, that means that we need to then flip the inequality. So this inequality now becomes a greater than or equal to becomes less than or equal to, because all of our signs will then change to the following. So now we have t squared minus t minus 6 is less than or equal to 0. Now what did we do to do that? Well, we multiplied the whole inequality by negative 1. And remember, to switch the direction of the inequality, when you multiply by a negative, to make this easier to deal with. You'll need to be able to solve inequalities like this more than a few times in a calculus course, so let's make sure you can solve these. The first thing we need to do is determine where the function is 0, and that's not too difficult in this case. We have t squared minus t minus 6. We're going to factor that to be t minus 3 times t plus 2, which is equal to 0. Now solving for t, the function will be 0 at t is equal to -2 and t is equal to 3. Now, these points will be the only place where the function may change sign. It's not required to change sign at these points, but these will be the only points where the function can change sign. This means that all we need to do is break up a number line into the 3 regions that avoid these 2 points and test the sign of the function at a single point in each of the regions. If the function is positive at a single point in the region, it will be positive at all points in that region because it doesn't contain any of the points where the function may change sign. We'll have a similar situation if the function is negative for the test point. So here's a number line showing these computations. So noticing what we found here, in our previous example, we had -2 and +3 are our testing points. And what it's done is it's created 3 regions. So we have region 1, we have region 2, and then we have region 3. Okay, and so in region 1, what we're doing is we're checking the point -3, which is what we're plugging into that function. And we want to find out whether it's going to be greater than or less than 0. So if we plug in -3, we get 9 plus 3 minus 6, which gives us 6. And therefore, this 6 is greater than 0. In region number 2, we're picking the value to be x is equal to 0. So we're picking 0 in this region. So plugging in for x, we get 0 minus 6, and therefore this is -6. So that means that this is less than 0 because it's -6. And in region 3, we're going to pick the value of 4. So plugging in 4, we get 4 squared, which is 16, minus 4, which is 12, minus 6 gives us +6. So therefore, this value 6 is greater than 0. So from this, we can see that the only region in which the quadratic in its modified form will be negative is in the middle region. Recalling that we got to the modified region by multiplying the quadratic by a -1, this means the quadratic under the root will only be positive in the middle region, so the domain for this function is the following. It's in between -2 and 3 inclusive. So therefore, we know that it's true in region 2 and then false for regions 1 and 3. So that means we have a bracket here, and we're including everything in between -2 and 3, which then represents our domain. Part C, we have h of x, which is equal to x over the square root of x squared minus 9. In this case, we have a mixture of the 2 previous parts. We have to worry about division by 0 and square roots of negative numbers. We can cover both issues by requiring that x squared minus 9 must be greater than 0. Note that we need the inequality here to be strictly greater than 0 to avoid the division by 0 issues. We can either solve this by the method from the previous example, or in this case, it is easy enough to solve by inspection. The domain in this case is x is less than -3 and x is greater than 3. So we have left parenthesis -infinity comma -3, right parenthesis, and left parenthesis 3 comma infinity right parenthesis. The next topic that we need to discuss here is that a function composition. The composition of f of x and g of x is the following. F composite g of x is equal to f of g of x. In other words, compositions are evaluated by plugging the second function listed into the first function listed. Note as well that order is important here. Interchanging the order will more often than not result in a different answer. So for example 6, we're going to be given 2 functions. We're given f of x, which is equal to 3x squared minus x plus 10, and g of x, which is equal to 1 minus 20x. And we're going to find each of the following. we're going to find f composite g of 5, f composite g of x, g composite f of x, and g composite g of x. So for the first one, f composite g of 5, we're going to first write the definition. So in this case, we've got a number instead of an x as an input, but it works in exactly the same way. So f composite g of 5 is equal to f composite g of 5. So what do? We first need to find what is g of 5. So g of 5 is plugging in 5 into the function for g. So it's going to be 1 minus 20 times 5, which is 1 minus 100, which is equal to negative 99. And now we have negative 99. And now what we're going to do is we're going to plug that 99 into the function for f. So now this is going to become f of negative 99. And then we plug that into 3 times negative 99 squared minus a negative 99 plus 10. And that gives us the result of 29,512. Next, we have f composite g of x. So f composite g of x becomes f of g of x. Now, g of x, in our example, is 1 minus 20x. And we're going to plug that into the function f now. So it's going to become 3 times 1 minus 20x minus 1 minus 20x plus 10. So when we square this, we get 3 times 1 minus 40x plus 400x squared. If we distribute the sign, we get negative 1 plus 20x plus 10. And now if we distribute the 3, we end up with 1200x squared minus 100x plus 12. Now compare this answer to the next part and notice that answers are not the same. The order in which the functions are listed is very important. Part C, g of f of x. G composite f of x is equal to g of f of x. Now let's note here that f of x is 3x squared minus x plus 10. So we're going to plug it into the function of g, which is 1 minus 20 times x, but we're placing x to be 3x squared minus x plus 10. So we distribute the negative 20 and get the result to be negative 60x squared plus 20x minus 199. And just to make the point one more time, this answer is different from the previous part. Again, remember that order is important in composition. In part D, g of x, in this case, do not get excited about the fact that it's the same function. Composition still works the same way. So g of x is the same thing. So we have g of x. Now remember that g of x is 1 minus 20x. And we're going to plug that into x for the function g. So it becomes 1 minus 20 times 1 minus 20x. If we distribute the negative 20, then we get the result 400x minus 19. Example 7. Given f of x, which is equal to 3x minus 2, and g of x is equal to 1/3 x plus 2/3, find each of the following. In part A, we want to find f composite g of x and g composite f of x. Well, f composite g of x tells us that the definition is f of g of x. So recall that g of x is equal to 1/3 x plus 2/3. So we're going to plug that in here. So now we're going to take this as the input and then plug it into the function f of x. So it's going to be 3 times x, which is now 1/3 x plus 2/3 minus 2. Now let's distribute the 3. Well, 3 times 1/3 x is x. 3 times 2/3 is plus 2. And then we get minus 2 at the end. Well, 2 minus 2 gives us x. Now let's find G, composite f of x. So this becomes G of f of x becomes the input, and f of x is 3x minus 2. And we're going to plug that into the function g. So it becomes 1/3 times 3x minus 2 plus 2/3. So let's distribute the 1/3 to those two terms. 1/3 times 3x is x. 1/3 times minus 2 is minus 2/3 plus 2/3. Minus 2/3 plus 2/3 is 0, so we get x. So in this case, the two compositions were the same, and in fact the answer was very simple. Both of these end up equaling x. This will usually not happen. However, when the two compositions are both x, there is a very nice relationship between the two functions. We will take a look at that relationship in the next section.